This is our video about the effect of intermolecular forces on boiling point and freezing point. We're also going to talk about heating curves and the delta H of vaporization and the delta H of fusion. In a previous video, we talked about the types of intermolecular forces. We talked about dispersion, dipole-dipole forces, hydrogen bonding, and ion dipole. But why do those intermolecular forces matter? Intermolecular forces matter because they greatly influence the boiling point and freezing points of compounds. When we're talking about boiling point, we're talking about the temperature that we need to take liquid molecules and separate them from each other so that they become gaseous. And the stronger the intermolecular forces are, the higher the temperature we need to create that separation. When we're talking about freezing points, stronger intermolecular forces mean that the molecules are more likely to stay as a solid and they have higher freezing points. Another way that intermolecular forces really matter is this rule called the like dissolves like rule. What the like dissolves like rule means is that polar molecules will mix together with polar molecules, and nonpolar will mix with nonpolar. But polar molecules and nonpolar molecules do not mix. That's basically oil and water. Now that's kind of the simplified version of the like dissolves like rule. What the like dissolves like rule really means is that things with similar intermolecular forces will mix. And how that works is a polar molecule will have dipole-dipole, and this polar molecule would have dipole-dipole intermolecular forces. And because those are similar, they will mix. Nonpolar would only have dispersion forces, and this one would only have dispersion. And because those are similar, they will mix together. But down here, the polar molecule would have a dipole-dipole, and the nonpolar would have dispersion. Because those are different from each other, they will not mix. Now, why do we care so much about this like dissolves like rule? Well, when you want two things to react with each other, it's really important that you can get them to mix together. So if we can look at a compound's structure and decide what type of intermolecular forces it'll have, we can tell what other things it will mix with. And that'll help us predict whether our two reactants will be okay mixing in the same container with each other. So just a little review of the types of intermolecular forces. We have those listed here, and we have their strengths listed here. Dispersion is the weakest. Ion dipole is the strongest. Now we can also see the effect on the boiling point. Because dispersion forces are the weakest, they are the easiest to boil. They have the lowest boiling point. Ion dipole is the strongest, and so their boiling points are the highest. It takes the highest temperature to get the liquid molecules or the liquid compounds to become gaseous compounds, to separate those molecules from each other. Now again, when we're talking about boiling something, we're talking about taking something in the liquid state, in which the molecules or atoms are pretty close to each other, and making it into a gas where the particles, those could be atoms or molecules, are really far apart from each other. So what we're trying to do is we're trying to move molecules away from each other. And the stronger the intermolecular forces are, the stronger those attractions are, the more energy it's going to take to separate them. If they're really attracted to each other, it's going to take a lot of energy to create that space. When we boil a liquid, we have to put in enough energy to overcome all the attractions between the molecules or atoms. So really what we're saying when we're boiling something is that we have to put enough energy in to break the intermolecular forces. And we know how to predict what type of intermolecular forces a molecule can have. But another way to test something's intermolecular forces is actually to measure the boiling point. And the higher the boiling point, the stronger the intermolecular attractive forces are. Now, another measure of intermolecular forces is called the heat of fusion or the heat of vaporization. These are numbers that we worked with when we were doing some thermochemistry in Chapter 6, but it's been a while since we've seen them. And I wanted to talk about what those names mean. So the amount of energy that is required to melt 1 mole of a solid is called the heat of fusion. I know that word fusion is kind of confusing because when I think of fusion, I think of things coming together. But the heat of fusion is what it takes to take solid particles, which are really close together, and turn them into a liquid where they're a little bit further apart. So it's the amount of energy that it takes to go from a solid to a liquid. And that's called a phase change when we're going between 2 different phases. So the heat of fusion, which we normally write delta H FUS, is the amount of energy it takes to do this phase change from solid to liquid. Now the amount of energy that it takes to go from a liquid to a gas, where the particles are really far apart, that one is called the heat of vaporization. And we normally write that as delta H vap, like that. Both of these energies are always endothermic. They're always positive. It always takes energy to make them happen. And they are not numbers that we memorize or that we really would have a lot of familiarity with, but we can find them in the appendix of the book. And I've looked up the ones that we'll need for today. If you've never seen one, I'd like to introduce graphs like this, which are called heating curves. Heating curves are graphs of the temperature of a substance versus how much energy you've put into that substance. If we look at this small heating curve, we can see that there's 3 segments. There's this diagonal portion here, there's this flat portion here, and then another diagonal portion. And different things are happening during each one of those. During any of the diagonal portions, like this one, what we're seeing is that the temperature is going up as we add heat. So what we're doing here is we're adding in energy and we're raising the temperature of the substance. But in this curve here, it flattens out at a certain point. And what's happening is we're adding heat, so we're making progress in this x-axis, but the temperature is not changing at all. During this flat portion, what's happening is we are taking a solid and we are making it into a liquid. So we're adding heat to break the intermolecular forces. We're adding energy to break the intermolecular forces, but all the energy is being used to break the forces and there's no more energy to increase the kinetic energy of the molecule, so the temperature is not increasing. Once all the molecules or atoms have been converted into the liquid state, then we can start adding more energy, and that energy will go to increasing the kinetic energy of the molecules, and the sample will start heating up again. So during these diagonal portions, that's where we're heating. During the flat portions is where we have a phase change. Now, if we wanted to calculate numbers for these different portions, It depends on what portion we're talking about. If it's a phase change, like this flat portion here, this would either be the delta H of vaporization or the delta H of fusion, depending on what the phase change is. For the heating portion, we use our thermochemistry equation that Q equals C times M times delta T. It has to do with the specific heat, the mass, and the change in temperature. So the amount of energy that we would put in would increase with how much temperature we want to increase. It would increase with the amount of mass that we're putting in, and it would increase with the specific heat of the compound. Here we have a heating curve that's a little bit more complete. It starts at a low temperature where we've added no energy, and we have a solid. We start putting in energy, so we start moving in the X direction, and during that we are warming. So if we're going in this direction, we are warming this solid up. Once it reaches its melting point, we're going to start putting energy in, and it's going to melt the solid into a liquid. So at this point here, we have just liquid molecules or liquid atoms. None of the solid has been left. Now if we continue to add energy, we would be heating the liquid, and we would heat it all the way till it reaches its boiling point, and at that point we would start converting that liquid into a gas, and that's what it means to boil. So at this point here, we've converted all of our sample to gas, and now we can heat up the gas. Here's what the heating curve looks like for water. If you start at negative 25 degrees, it's going to be a solid. So we have our ice there. So if we start adding in energy going in this direction, we're going to start heating up that ice until it reaches its melting point. And when we reach the melting point, what we've done is we've created a solid sample that's at the melting point, which for water is 0 degrees. Once we've reached that point, if we continue to add in energy, what we're doing is breaking the intermolecular forces. So during that portion there, we're going from a solid, converting it into a liquid. We call that amount of energy the delta H of fusion. So I've actually looked up that number, the difference between these two, and the delta H of fusion for water is 6.02 kilojoules per mole. So if you want to do 1 mole, it costs 6 kilojoules. If you want to melt 2 moles, it costs about 12 kilojoules. Now, once you've converted all the solid water into liquid water, which is what we've done when we've reached this point here, at that point, now you can start heating up the liquid water. And to heat up the liquid water, it costs 4.18 joules for every gram you want to heat up, and for every degree Celsius you want to increase its temperature. That's called the specific heat of water. Up here, when you've heated up the water until it's reached its boiling point, at this place here, what we're going to do is we're going to take liquid water and we're going to turn it in to gaseous water. So we're taking liquid and we're making it into a gas, and once we've reached this point, all of our sample is a gas. So again, all this energy here goes into breaking the intermolecular forces between the liquid molecules and allowing them to separate from each other to become a gas. Once all your sample is a gas, now you can heat up the gas, and that can go until kind of a high temperature when it would actually become a plasma, our fourth state of matter. Before we do any calculations, I just want to point out the relative sizes of these delta H's. This one here, the delta H of fusion, so that's how much energy it takes to melt solid water into liquid water. And this one is the delta H of vaporization. That's how much energy it takes to make liquid water into gaseous water. Look at the size differences there. The delta H of vaporization is huge compared to this delta H of fusion. And I had looked up the numbers for the heat of fusion and the heat of vaporization down here at the bottom. The heat of fusion, this portion right here, is about 6 kilojoules. This portion here is about 40 kilojoules. That's like 6 or 7 times higher than the delta H of fusion. So why is the heat of vaporization so much bigger than the heat of fusion? Well, let's think about what's happening during these two processes. During this one here, we're going from solid particles, which are really close together, to liquid particles, which are a little bit further apart. And during this process, we're going from liquid to gaseous, where they are extremely far apart. Now, both of these are talking about breaking the intermolecular forces. When it's the heat of fusion, we only need to separate them just a little bit, right? We only need to make a little bit of space between the particles, not that much more space than they had before. So the change in this one is a lot smaller, and it takes less energy to make those separations. But up here, going from a liquid to a gas, the change is very big. Here they had a little bit of separation. Here they have a ton of separation. And that means breaking a lot more intermolecular forces, breaking a lot of attractions. So because the space that we need to create up here is so much bigger, it takes more energy. And that's why our delta H of vaporization is so much bigger than our delta H of fusion. And what I'd like to do is I'd actually like to do a calculation where we go through and we calculate how much energy it takes to do this segment. How much energy does it take to heat up the ice? How much energy does it take to melt the ice? How much energy does it take to heat up the liquid water? How much energy does it take to boil the water? And then how much energy does it take to heat up the steam or heat up the water vapor? And we'll do it just the way it has it on the graph here. For part 1, we're heating up the ice, and so we will need to reference this specific heat of ice to do that. For part 2, we will be melting the ice, and so we will reference the delta H of fusion. During part 3, we're heating up the liquid water, and so we'll need the specific heat of liquid water. During 4, we're going to be boiling the water, so we'll need to use the delta H of vaporization. And during 5, we'll be heating up the steam, and so we need to use the specific heat of steam. Now, all of these numbers down here are not numbers that you would know off the top of your head. They're all numbers that I got from our appendix in our book. So we're going to do this calculation. We're going to figure out how much energy it takes to heat 1 mole of ice from negative 25 degrees all the way to making it steam at 125 degrees. And we're going to do it in different segments. So there's going to be 5 of these following our heating curve. In our first part of the heating curve, we are heating 1 mole of ice at negative 25 up to the melting point, which for water is 0 degrees. The equation that we use anytime we're heating something up is that the energy, Q, is equal to the mass times the specific heat times the change in temperature. So we need to know the mass. And our problem says that we have 1 mole of ice. 1 mole of ice is equal to about 18 grams. And the way that I did that is I said 1 mole of ice, and ice is water. Ice and water. 1 mole is 18.02 grams. So that's just the molar mass of water. And so in these slides, I really should have put 18.02. So now I have my mass. I would then look up the specific heat of ice, and this from the previous slide is that. And then I need to calculate a delta T. Remember, delta T is always final minus initial. So when I put that into my equation, like this, my T final is 0 degrees. I'm raising it to the melting point, and I started at negative 25 degrees C. So this is my final, this is my initial. And when I did that, I got the energy was about 941 joules. Now you can do this in joules. The reason I got joules is because grams cancels out with grams, degrees C cancels out with degrees C, and I'm only left with joules. I could also put this in kilojoules if I needed to. I would just divide by 1,000, and that would be 941 kilojoules. So either one of those answers is right. Okay, so now I want to do segment 2, which is melting the mole of ice at its melting point. So that would be 0 degrees for water. The way that we calculate the energy there is we say that the energy is equal to the number of moles times the heat of fusion. So for us, Q is going to be equal to the number of moles, 1 mole, times the delta H of fusion, which I looked it up. It was on the previous heating curve slide, like this. Now the units cancel out here, and I get kilojoules. And what I get on my calculator is just 6.02 kilojoules. Okay, segment 3 is we have just melted all that ice, and now we're heating up the water that we've created. It's starting at 0 degrees, so that's the melting point, and we're trying to get it all the way up to its boiling point, which is 100 degrees. So if you're keeping track on the heating curve, we've already done this one. We've already melted our ice, and now we're heating that liquid water up. Anytime we're heating something up, we use this equation, and we already know our mass. Our mass is 18.02 because we just have a mole. But the specific heat of liquid water is a little bit different than the specific heat of ice. They actually have different numbers there, so we want to make sure we use our specific heat of liquid water. And then our change in temperature is always going to be final minus initial. So we do it like this. And then when we do our temperature, the final is 100 degrees, and our initial was 0 degrees. So on my calculator, I got 7.52 times 10 to the third joules. And if I put that in kilojoules, it would be 7.52 kilojoules. So either one of those is right. All right, so now we're on segment 4. And if you're following along with our heating curve, we heated up the ice, we melted the ice, we heated up the liquid water made from that ice, and now we are boiling that water. We use the equation that the amount of energy is equal to the moles times the heat of vaporization. It makes it kind of easy because we only have 1 mole again. And I looked up the delta H of vaporization. It's kilojoules per mole. Moles cancels out, and I get that it takes 40.7 kilojoules to boil our water. Okay, and we are now at the last segment, which we were just boiling here, and we've done that. Now we are heating up the steam that we've created. Anytime we heat up, we're using this equation, and so I have my mass, and that was 18.02, because I have 1 mole. The specific heat of steam is lower than the specific heat of water. It's actually easier to heat up steam than it is water. And now I have to do my delta T. It's always T final minus T initial. I'm trying to get to 125 degrees from 100 degrees. So 125 is my final, 100 is my initial. And when I do that on my calculator, I got 904 joules, or 0.904 kilojoules. All right, so I have calculated the amount of energy for my last portion up here, this heating up the steam. What I want to do now is I want to go back and I just want to take each one of these that we did and I want to add them all together. All right, so I've drawn us our little heating curve here, and I've kind of written down what each one of these segments was. Now if I add in the energies, so this one was 0.941 kilojoules, this one was 602 kilojoules, this one was 7.52 kilojoules, this one was 40.7, and this one was 0.904 kilojoules. And if I add those up to get a total, I get 56.085 kilojoules. And it looks like I should only have, when I'm adding things together, I should only have one place past the decimal. So this would be 56.1 kilojoules total. In this video, we talked about why intermolecular forces are important. We talked about their effect on boiling point, freezing point, the delta H of vaporization, and the delta H of fusion. And then we also looked at heating curves, and we did a calculation to figure out how much energy it takes to melt, so the energy it takes to heat things up, to melt, and boil substances.